Okay, in this lesson today, we're talking about parallel lines and triangles. What we're going to do, I'll give you a brief summary before we get started. We're going to prove that the angles in a triangle add up to 180 degrees, and we need a parallel line to prove that. So that's why we're doing this now, instead of waiting until we get to triangles. We'll also introduce exterior angles, because you might not have seen those before in triangles, but that way we have all of our triangle sum theorems in one lesson. So before we get started, we need to look at this postulate. It's parallel auxiliary line postulate. That's not really the name of it. It doesn't have a specific name, so I just gave it something that kind of tells what it is. But very seldom will you need to use this, so don't stress over trying to memorize this name. Because like I said, it's not its real name. It says, through a point not on a line, there is exactly one line through that point parallel to the given line. So the given line is the line that the point's not on, and we can draw one line. There only exists one line that's parallel that goes through that point. So here it is as a picture. Here we've got, we'll call this point A, and we'll call this line BC. We can draw one line, and we typically do these as dotted lines because we're adding them in. It's called an auxiliary line. That's why we have that word auxiliary there. And I'm going to put point D on there just so I can give that line a name also. So we know that line AD is parallel to line BC. It doesn't matter how many times I repeat this process. Even if I give the line a whole bunch of different names, it's still the same line as long as it goes through point A. Only one line exists there. So the triangle sum theorem, and you learned this years ago. You didn't give it the name triangle sum theorem, but you already knew this. The sum of the interior angles of a triangle is 180 degrees. Like I said, you've known that, you learned that in elementary school, but today we're going to prove that that's true. There's a lot of things that you were taught and you accepted them as fact. That's what your teachers asked you to do, and that's great because you were not yet ready to prove things. But this one we are actually going to prove here in a few minutes. But first, let's just throw this into action, some very simple problems. If we want to find the missing angle, we'll call them x just so we can put them into an equation. We have two of our angles. So if we add x plus 38 plus 58, we know that's going to add up to 180. That's x plus 96 is 180. So our missing angle is 84 degrees. In B, x plus 27 plus 27 is 180. Combine like terms, that's x plus 54. And so our missing angle is 126 degrees. Okay, easy peasy, lemon squeezy. All right, now what is not so easy is proving it. And it takes 7 or 8 steps. It's not terribly difficult, but there are things on here that most people don't just naturally think, hey, let me do this. And in order to prove this, it requires creativity. So far in math, a lot of you haven't been able to use creativity, but you have to come up with things that aren't obvious to you all the time. So first thing is, notice that I made a typo. When I was copying in my first line, I accidentally copied the prove statement instead of the given statement. So all we are given is triangle ABC, and you can see it in the picture there. That's all we have. We don't have anything else but triangle ABC. And our reason for that is given. Now this is where that parallel auxiliary line postulate comes in. We're going to add a line to our picture. So I'm just going to say draw CD parallel to AB. So I'm drawing a line. I'm creating a line because it's line CD. I know it goes through point C, and I have to add another point D to it. And That's parallel auxiliary line postulate. And again, that's not a real name. I did it just because it's easier than writing out. Through a point, not on a line, there is exactly one parallel line, one line parallel to the given line. So let me draw my auxiliary line in here. Okay, and I know I need point D on here because I called it line CD. And I know that this line is parallel to that line. So now, and that's one of those things that most people will not think to do if they were trying to prove this on their own. So since we know that those two lines are parallel, we have two parallel lines and we've got two transversals. So AC is a transversal and CB is a transversal. That's why we're doing this now, because we just talked about transversals and parallel lines. To make this a little bit easier, I'm going to label my angles 1, 2, 3, and then I'm going to call this one 4 and this one 5. That just makes it easier to write it down in the proof. And we know if we have AC as a transversal, we know angles 1 and 4 are congruent. So angle 1 is congruent to angle 4. We also know that if CB is a transversal, that 2 and 5 will be congruent. And both of those are true because they are alternate interior angles. So our reason for that is the alternate interior angle theorem. Now, if they are congruent, what does that mean? What do you know about congruent things? They have equal measures. So we can say the measure of angle 1 equals the measure of angle 4, and the measure of angle 2 equals the measure of angle 5. So, and that's definition of congruent angles. Now, to move forward from here, we're just going to look at that top angle, that top set of angles, these up here. Now, we can't say that 3 angles add together to get 180 degrees directly. What we need to say is that angle 4, the measure of angle 4 plus, I need to do this a different way. The measure of angle 5 plus the measure of angle BCD is 180 degrees. So the two angles that I've outlined there in purple, those form a linear pair, and the linear pair postulate says that they are supplementary, they add up to 180 degrees. So, but we also know that angles 3 and 4 add up to give us angle BCD. So the measure of angle BCD is equal to the measure of angle 4 plus the measure of angle 3. And that's angle addition postulate. So we can take these 3 and replace BCD, or excuse me, these 2 and replace BCD with that. So now we have angle 5 plus angle 3 plus angle 4 equals 180 degrees. That tells us that these 3 angles add up to 180 degrees. And that was substitution property, because we substituted 3 plus 4 for BCD. Now, last step, and this brings us full circle, we know that, let's see here, we know that 2 and 5 are equal, so we can do that. Replace the 5 with the 2. We know 1 and 4 are equal, so we can replace the 4 with the 1. I'm going to erase those so that I can actually write here. So because we can do that, those two substitutions, we know that 1 plus 2 plus 3 is 180 degrees. Again, that's substitution. And that's not what our proof statement is, but angle 1 and angle A are the same angle. So that's the measure of angle A. Then angle 2 and angle B are the same angle. And angle 3 and angle C are the same angle. So we didn't really do an extra step there. We just changed the names around. And it's because I had labeled my angles to make it easier. So that's not really an extra step. I'm just doing that so that I can get back to my proof statement. So, using one auxiliary parallel line, you are able to now prove something that you learned in elementary school. That the three interior angles of a triangle add up to 180 degrees. Now, even if we hadn't solved that, you would be able, or proven that, you would be able to solve these next problems anyway. Add our three angles up to get 180, just like we did earlier. 4x plus 2 plus 60 plus 70 equals 180. So that gives us 4x plus 132, combining like terms. 4x equals 48, so x is 12. For B, same setup, 5x plus 70 plus 60 equals 180, so 5x plus 130 equals 180, and 5x equals 50, so x equals 10 there. And it doesn't matter which order you do your angles. Adding is commutative, so you can write them down in any order. You're still going to get the same answer in the end. Now, something that may or may not be new for you for the rest of this lesson. Exterior angles of a polygon. If you extend one side of a polygon, I'm going to do this with a pentagon. It works with any polygon. If you extend one side, then you get an exterior angle. It's the angle between that extension and the side next to it. And it's always going to be the smaller of the two angles. Here we have a 180 degree angle, not the smaller, but it's going to be the one that's not 180. So we've got a straight angle there, so it's going to be the other angle on the outside. That's the exterior angle. In these three pictures, angle 1 is shown as our exterior angles. We also have remote interior angles, and those are the two angles inside the triangle that are not adjacent to our exterior angle. And in these pictures, that's angle 2 and angle 3. So you can see these two are not adjacent to, they don't share a side with angle 1. Same thing in each of these pictures. The triangle exterior angle theorem tells us that that exterior angle, angle 1, is equal to the sum of the two remote interior angles. So let me write all that out. The measure of an exterior angle of a triangle is equal to the sum of the measures of the remote interior angles. And so using our pictures up here, what that means is for each of these, the measure of angle 1 equals the measure of angle 2 plus the measure of angle 3. So the exterior angle equals the two remote interior angles added together. So if we wanted to find our missing angles in example 3, we have the exterior angle, that's the 110, equals the other two added together, the remote interiors added together. So that's x plus 50. So x would be 60 degrees on A. On B, notice our exterior angle is the one that we don't know. So we have x equals 50 plus 98. So that exterior angle is 148 degrees. So if you know your two remote interiors, you'll add them together. But if you know one interior and the exterior, you'll subtract to get the other one. All right, so for our last example, we're going to find all of these different variables, and we just need to do them piece by piece. If you look right here to find C, that might be the easiest one to start with. We know that those two add up to 180. So the measure of angle C, or actually it would just be C equals, not measure of angle. C is 180 minus 55, which is 125 degrees. So if that's 125, then we know that C and 32 and D have to add up to 180 because those are the three angles of a triangle. So D has to be 23. So we can fill that in. If you look over here at E and B, well, if this angle, angle EFG, is 90 degrees, then we know this one also has to be 90 degrees. So we know E is 90. We also know that these two together have to add up to 90 degrees. So we can figure out that B is 58. So if B is 58 and FHG is 55, we know that these three add up to 180. So we can go back and find that A is 67. And that gives us all of these angles. So, in summary, inside angles of a triangle add up to 180 degrees. You already knew that, but now we've proven it. And the exterior and exterior angle of a triangle is equal to the sum of its remote interior angles. So try those practice problems, check over your work, ask questions, and then get ready for that mastery check. Good luck.